Welcome to This Explainer. Today, we're diving straight into the absolute physical backbone of the modern internet. We're going to explore how we've essentially engineered light to carry terabits of data across the globe. We'll be decoding the physics, the architecture, and honestly, some of the wild hardware choices that make our connected world possible. So let's just jump right in.
Think about the device you're watching this on right now. The data reaching it actually traveled through something astoundingly common, and that's sand, literally. Over 26% of the Earth's crust is made of silicon dioxide. And yet, by hyper-purifying this everyday dirt into absolutely flawless glass, humanity managed to build the entire nervous system of the modern world. It's kind of mind-blowing when you think about it.
Now, sure, fiber optics might feel like a magic bullet. I mean, they bring massive bandwidth, ultra-low transmission loss, and zero electromagnetic interference, but there's a pretty steep trade-off here. Engineers are constantly battling severe physical constraints. You can't just bend glass like you can copper without all the light leaking out. Plus, cutting or splicing these cables, that demands microscopic precision and some highly specialized tools. So let's zoom inside a single fiber strand. What we find is a microscopic architecture built for one singular purpose: protecting that light. Right at the dead center is the core, and that's what actually carries the optical signal. Surrounding that is the cladding, which basically limits the direction the light can travel. Then we've got a protective coating, usually a resin or rubber, just to give it mechanical strength. And the whole shebang is wrapped up in a tough outer jacket. But how does this structure actually work? Well, it all comes down to a really brilliant physics trick: total internal reflection. By giving the core a slightly higher refractive index than the surrounding cladding, a photon hitting the boundary doesn't just pass through, it bounces. The cladding basically acts like a perfect mirror. It traps our data as it shoots forward at incredible speeds. To really see how data moves globally, we can track a single optical signal through three distinct phases. First, its birth at the transmitter, which turns electricity into light. Second, its perilous journey through the transmission medium, the glass fiber itself. And third, its arrival at the receiver, where it gets decoded right back into the digital data your device needs. Following that exact life cycle, an electrical signal comes in, hits a driver circuit, and triggers a laser, like an LD or V-cell, to fire. That light is then pushed out into the passive fiber, occasionally hitting amplifiers along the way, just to give the signal a much-needed boost. And finally, photodetectors, using tech like PIN or APD components, catch those tiny photons and convert them straight back into a clean electrical signal. But hey, make no mistake, the journey through that glass isn't exactly a walk in the park. As our signal travels, it battles two primary, totally invisible enemies. The first is attenuation. This is the sheer, brutal loss of signal energy as the glass absorbs and scatters the light. The second enemy is dispersion. Now, dispersion doesn't weaken the signal, but it actually distorts the shape of your data. So when attenuation hits, a crisp, strong square wave dangerously fades away over distance. The data's shape stays intact, but the energy becomes incredibly weak. Dispersion, on the other hand, way messier. Because different wavelengths or modes of light travel at slightly different speeds, those crisp waves stretch out over long distances. They eventually overlap and completely scramble the message, creating a total nightmare known as intersymbol interference. Knowing these enemies are out there, engineers mapped out exactly how light behaves in glass and hunted down what we call the golden bands. They found this absolute sweet spot at 1310 nanometers, where dispersion is virtually zero, making it perfect for high-speed mid-range hops. Further down the spectrum, at 1550 nanometers, there's this massive dip in attenuation. That ultra-low loss rate makes 1550 nanometers the undisputed king for long-distance backbone networks. But to really fix these problems, engineers literally had to evolve the glass itself. The standard G.652 fiber was great for short runs, but it suffered from high dispersion at that crucial 1550 nanometer band. They tried fixing it with G.653, shifting the zero dispersion point exactly to 1550. But whoops, that accidentally created a catastrophic new problem: severe nonlinear effects, where signals essentially start interfering with each other. So the ultimate fix? The G.655 standard. They purposefully engineered the glass to retain just a tiny calculated bit of dispersion. It acts as a buffer to suppress those nonlinear effects, and that's exactly why it's the standard for long-haul networks today. Now, to power light through this incredibly specialized glass, you need the right hardware engines. Think of it like an arsenal of tools. For short jumps around a data center, cost-effective FP lasers totally do the trick. But for ultra-long transatlantic leaps, you're going to need the incredibly narrow, high-power beam of an EML laser. And on the receiving end, sure, a standard pin diode works for most jobs, but extreme long hauls require avalanche photodiodes, or APDs. These give you extreme sensitivity to catch the absolute faintest, most distant signals. So here is the big question for you. Knowing the physical enemies of attenuation and dispersion, and having this specific menu of active hardware and glass types, how exactly do network engineers combine them to beat the physical limitations of the natural world? Well, the answer is brilliant engineering synergy. To beat the energy loss of attenuation, engineers pair high-output lasers with those hypersensitive APD receivers, and then they drop optical amplifiers along the route to boost the light. To beat the signal distortion of dispersion and nonlinear effects, they deploy that highly specialized G655 fiber. See, breaking distance limits isn't magic at all. It's just the perfect harmony of source intensity, medium purity, and receiver sensitivity. But, while we all obsess over high-tech lasers, we really can't forget the network's silent foundation, unpowered passive components. They don't plug into a wall, but the network completely fails without them. We rely on high-precision connectors to seamlessly join cables, attenuators to protect sensitive receivers from getting literally blinded by powerful lasers, and multiplexers. These act like prisms, combining multiple colors of light to maximize the massive data capacity of just a single physical cable. If we track the real-world evolution of the transceivers that engineers are actually plugging into servers, the pace of change is just staggering. We started out in the gigabit era with these bulky, basically brick-like GBIC modules. But as data demands exploded, we rapidly transitioned through smaller XFP modules into the really compact SFP Plus standard for 10 gigabit speeds. And today, we rely heavily on dense QSFP modules to push 100 gigabits and well beyond. This whole hardware evolution highlights three basically unstoppable trends. Number one, a relentless exponential increase in transmission speed. Number two, continuous physical miniaturization. Real estate in a data center is incredibly expensive, right? So engineers have to pack more connections into every single server rack just to keep up with our digital consumption. And number three, smarter digital diagnostics. We're now allowing these tiny modules to report their own temperature and laser health in real time. Which leaves us with a final thought to ponder. We've taken literal sand, bent the laws of internal reflection, and engineered lasers to shoot terabits of information across ocean floors. But as our global data demands continue to skyrocket with things like AI and spatial computing, we are eventually going to hit the ceiling of what even the best glass can do. So what new, invisible physical limits will the next generation of engineers be forced to conquer? Thanks for joining me on this explainer. I hope it illuminated the incredibly complex world operating just beneath your internet connection.